thank you everyone for joining today. Really excited to bring you this webinar around multi-material printing with the ARBURG Freeformer platform. My name is AJ Strandquist. I'm the CEO at Würth Additive Group. We're a company that helps customers digitalize their inventory management and utilize platforms just like the Freeformers in their own building to save time, effort, and money. With that, I have two colleagues with me, which is Gerry and Jacob. And they will be your main custodians today, kind of taking you through everything. So I'll hand it over to Jacob first.
Yeah, thank you, AJ. I appreciate it. So I am a 3D print engineer with the Würth Group. I'm actually going to be focusing on especially the material side of these things on this discussion of multi-material printing today. And then with that, I'll let Gerry go ahead and introduce himself as well.
Hi, my name is Gerry Berberian. I am with ARBURG Additive. And I'm excited to show you a little bit about multi-material printing today. So Jacob, please feel free to kick it off.
Awesome, thank you, I appreciate it. So with multi-material printing, there is a huge scope that we're looking at. So I'd like to go ahead and set the framework and set the stage for what we're going to be discussing today. First off, you could be looking at ceramics, metals, composites such as carbon fiber. What we're specifically focusing on are thermoplastics, or just plastics that you'd see in day-to-day life. Over 90% of the multi-material manufacturing that we're going to be seeing in the world is going to be this injection molded process. So we're going to be looking at parts that are comparable to that and that kind of style, where you've got maybe, as you see on the left, a base. This is a nozzle. This is two different materials. Obviously, it's got two different colors there. It could even be the same material with different colors, whatever you want. But basically, we're having that base component of a substrate is what I'll refer to it as. And the substrate is something where you deposit or inject onto that base component another component to make a multi-component part into one consolidated part. Okay, so it takes something that may normally require assembly. It reduces the steps of manufacture, and it increases the bonding strength of that. So that's what an example of what we're looking at and what we're talking about today is on the left. But there are a few different types of injection molding that can accomplish this. I've listed overmolding and two-shot molding on the screen right here. Really, they're very similar to one another. It's just semantics on the differences. But the big differences between insert molding, which you're inserting something like a cable or some hard metal structure that's a crucial component, something like that, and then molding over that with plastic. Or you have, say, overmolding, which you've got a plastic component, and then you're switching and putting more plastic over and letting it solidify. And that's what's kind of described on the right. And that image number 2 on the right-hand side of the screen, we've got a traditional, just general setup for one of these machines that could accomplish it. And this is just to serve, I won't dive too deep into the technical of how it's accomplishing this, but you can see barrel A, B, and C. And then in the finished part on the left side of that schematic, it says material A, B, and C. Basically, it selects times to input this material into that cavity to get a multi-material component. And it's a very complex system. As you can see, even from a simple schematic, it looks kind of confusing. There's a switch-off valve. There's all sorts of stuff going on there. But this is all to serve in setting up that stage for what we're going to be talking about. With that, I'll continue on to the next slide, and we're going to be getting into some of what it actually looks like on a if I'm having a mold made, if I'm a manufacturer saying, okay, I'm making this part, what actually is happening? And with injection molding, there's an entire industry devoted to this itself. There are conferences just on injection molding, so I'm not going to be deconstructing the entire process, but this serves to give you a representation and an understanding of how would I accomplish something like a toothbrush or a power drill that has multiple different materials on it. It's obvious you can grab something that's got a rubber grip, and yet it's got hard, rigid, strong housing to it, so it doesn't damage the internal components. How am I getting that done? This is just a start to that. On the left, all these different parts. This is an assembly file for some CAD program, and this is showing that there are a lot of moving components. It's got to inject these parts once they're done. It's got to move them around. It's got to switch automate it. Otherwise, it doesn't make sense. It's got to line up perfectly and mate perfectly, or else there are a ton of issues that come up. There are things that are very complicated with this process. And then, as you can see on the right in that image number 4, we're actually looking at what kind of hardware are we talking about? What scale is this? And it can range from, in cost, from a simple cavity being $5,000 to machine out, to normally with the more advanced multi-cavity ones like the ones on the right where you're making multiple parts at a given time. It can range from $25,000 to over $60,000 for a single mold. And that's on top of the idea, and it'll be different for every single part that you've got. You have to have a new one. And that's not even considering things like hardware. So point being, this is something that's very costly to get into, and it's something that's significant, something that, to get a simple product like a keychain with electronics housed in it, it could be something that actually is very intensive and laborious to actually achieve that product. One thing I'd like to note before we move on is that steel on the right that you see. If I'm commissioning a mold maker to produce this, and I'm having a part made, and I draw it up in CAD, and I'm still in that design phase where I want to make 100,000 of them, but I haven't done it yet, and I'm making a mold for it. And I make that mold. They add what's called steel safe, is the term used frequently. They add too much material on that mold cavity on purpose, with the understanding that their tolerances aren't going to be right. They're going to fail at that, or they can, and they need to machine out, so they're giving themselves a little bit of a window. But the fact that they have to draw that into the design consideration of making this mold underscores the fact that it's a process that's not perfect. It's something that it's very costly to get it wrong, and you have to be able to get it right. You can weld material back on, but if I've got an 8-week lead time, it just adds to that. It's never just 8 weeks. It's something where it takes even longer. With that said, I'll go ahead and address some of those. I mentioned some concerns that can pop up in multi-material and just in injection molding. I've listed some on the left here, such as sink marks, which we'll have an image of in just a second. This is something that, these are technical things. If you have any questions, feel free to contact me. My email will be at the end. I can talk about some of this. I love talking about it. It's not a big deal. So sink marks, it's just something that comes with cooling. It's a common known problem in injection molding. It's the part of the cooling process affects this and the thickness of the part. And you also get into things like warpage and weld lines, and you'll see knit lines where it can complicate stuff where differences in flow can all of a sudden pop up a really big issue. Flashing, as we've shown here on the screen, is something that's common. If you ever had an Army Men soldier or toys as a kid, especially with some of the cheaper ones, you'll see flashing on the part. That's inherent to it. And with multi-material, it's exacerbated actually, because it's you have to design for this. It's not that you're having to remove this. It's not that it's just a common issue because I did something wrong in the actual process. I have to design for it ahead of time, and it can be difficult. Moving forward beyond that, though, there are other things like short shot. This is when the cavity doesn't completely fill. Point being, there are lots of different things that can come up. If we see the schematic on the right, we're looking at core insert B. I'd like to draw some attention to that. Basically, these are parts that in multi-material print or manufacturing with injection molding, I'm printing that blue incomplete part A. Or not printing, I keep saying that. I'm focused in the industry. I'm manufacturing that and I'm injecting that into the mold. And then when it's done, I'm adding more to that. How do I do that? I'm moving it literally to another cavity. I have to have multiple cavities for the same part because it's got to be stepwise. It's got to be component based, and I'm doing one, and then it's got to fit into the other, and then I'm literally injecting over that part. Something that can come up, as you see with the ones on the right. The blue one is just a simple one, incomplete part A, and then complete part AB. It's putting material over that. And if I'm using a different base material for that blue part, something that's flexible, something that gives under pressure, and then I turn around and apply thousands of pounds of pressure to that part, it can fail. You're restricted innately in some of these design considerations for injection molding. It doesn't let you have full control over the process. All those issues on the left, they play into that design process. I mentioned wall thickness. You can't have variable wall thickness very frequently in an injection molded part. It doesn't work well. It doesn't play well. So people just know that in the industry, and they act like that's something that you have to just be smart enough to account for. But in reality, maybe it's something that you want to be able to overcome it and still design what would be best for the users or the end user or in your process. This is all to say there are lots of considerations, and maybe some of those are, overcomable. One that's not, though, is material compatibility, which I'll talk about. I pull up this chart. This is just something that also says there's a lot going on, both on the chemistry side as well as the mechanical side. And this is something that's in the 3D printing process, especially as well. ABS, with nylon 6, is that compatible? It is, but some of these others maybe not. So something as base as materials, if you pick the wrong things, you're destined to fail because you'll have an immediate, part failure. It won't have that strong interface I was talking about before. You would have rubber on your toothbrush just peel away. It's not desirable. So you got to have an understanding of that as well. Again, if you have any questions on this, feel free to reach out to me, and I talk more on this. But this is getting more and more technical, so I will leave this for another one of the webinars. But this goes and sets the framework for what we're looking at and comparing some of what we're going to be talking about today on the ARBURG parts. With that, Gerry, if you'd like to take it from here, I'd be happy to hand it over.
Thank you very much. I appreciate that introduction to multi-material, two-shot, and overmolding. So that brings us into the ARBURG plastic preforming process. Here's an illustration of the APF process for short. You may have noticed that a portion of it looks similar to a molding machine. So that's no coincidence. As ARBURG's main business is injection molding, and they've been doing it for over 65 years, they use that material processing knowledge to create the freeformer. The process starts by loading standard molding grade thermoplastic pellets into the hopper at the top right. The system has active drying to keep pellets dry while they wait to be printed. The material then flows through a screw and barrel as it's plasticized or melted, and then it enters our printing head, where a piezo opens and closes the nozzle to create a string of microdroplets. We use microdroplets instead of a filament because we can achieve a far higher density with droplets. The droplets are printed, and layer by layer, we start to see a part form. The printing nozzle stays fixed, and the tray moves underneath, carrying the part. Some additional notes about the process. We do have relatively high temperature range. We can get that nozzle up to 450 degrees C or 842 degrees Fahrenheit. And the build chamber, which you'll see in the next slide, we can get that up to 200 degrees C or 392 degrees Fahrenheit. Also, you might be interested to know, on the average, we're using a 0.2 millimeter layer size for our printing droplets. Creating multi-material parts using real thermoplastic materials is what makes the ARBURG Freeformer a unique offering in the additive industry. If we look at the system image, we can see how it manages that task. The key is 3 individual nozzles, each capable of printing a separate material. And when used in concert, 3 materials are extruded into a single build. The build tray is housed in a temperature-controlled environment that can maintain temperatures up to 200 degrees C. So this opens us up to a variety of materials, starting from your standard plastics, such as an ABS, a PC ABS, maybe a TPU, all the way up to our high temperature engineering plastics, such as the Ultim family. If we look over on the left-hand side, we see a bicycle brake lever and a housing with an integrated gasket. These are 2 examples of the virtually limitless combinations possible. If we look at that plate and gasket, what we see is a red ABS and a translucent TPU used together. You can also see our water-soluble support material is displayed underneath the overhang. Our process utilizes support material where it's necessary, and that support material is water-soluble. That's right, just warm water, no chemicals needed. Material combinations can be made of rigid and rigid materials, flexible and flexible materials, or rigid and flexible materials. Whatever your overmold or material combination needs, as long as they're thermoplastics, the freeformer is up to the task. So let's take a look at our first example. If you're a baseball player or you played in the past, you're probably familiar with DeMarini bats. DeMarini is a Wilson sports company and sells some of the best bats available on the market. Their R&D manager reached out to ARBURG some time ago to see if we could help with a problem he faced. When designing aluminum or composite bats, the end caps are made of a proprietary plastic. To test new cap designs, the engineers create a model in CAD, get a molding tool cut, and injection mold a handful of parts. This process takes 12 weeks from art to part, as the R&D manager coined it, and was the only way we were able to test designs and their materials. He was searching for a way to offer the engineers more options, to innovate and to try new designs before settling on one and heading into production. The biggest problem turned out to be manpower. Buying new milling machines and molding machines was a simple solution to open up capacity for the designers, but finding operators was a real struggle. So they decided to look at other options. 3D printing quickly floated up to the top as a way to get around creating tools the traditional way. Metal printing can create tooling without having to machine it. Some polymer printing can also create a tool for low volume of molded parts. There's also a company that prints a dissolvable mold. All of these are decent options, but they weren't a complete solution because the process would still require the molding of the parts. The manager reached out to ARBURG to see if the freeformer could skip the entire process and go from art to part, printing end caps in their proprietary material. They shipped some of their material to ARBURG's test center, and with little tuning, the freeformer printed their materials in no time. An end cap was placed on a bat and then fitted into a jig they used for testing the durability of those caps. A baseball was fired at 150 miles an hour at the bat 50 times in a row. At that point, the manager was comfortable with the freeformer's technology and its ability to print their materials. As you can see, the end caps come in multiple materials and color designs.
And Gerry, as you show it getting beat up, is I just want to add is, you can't lose that point that, you mentioned that 3D printing rose to the top because it was known as rapid prototyping, right, for 20 years. So it makes sense, but I think rapid prototyping and rapid validation, and validation very much includes the end material you're going to use, are two different things. If you print that on a off-the-shelf filament that you can buy anywhere, yeah, you can replicate the shape, but you might not be getting the dynamic properties, and you're also not validating on the material you want. So you just can't lose that point of how open and flexible ARBURG is to be able to print at those high densities in multiple materials. And oh, by the way, if you're making walkie-talkies, if you're making baseball bats, you can go that art to part on your material. It's such a big point. It's hard not to just make sure it's highlighted.
Couldn't agree more, AJ. Thank you. Let's take a look at the next example. So this is an example of a multi-material tool. It's an end-of-arm tool that ARBURG uses in their own manufacturing facility. You can see here a green part, which is a handle that ARBURG uses in a variety of panels that fit on their molding machines and accessories. Prior to automation, when the handle was molded, the part itself and the sprue would eject into a bin. They both fall in together. Once that bin was full, a person would remove the bin and replace it with a fresh bin, and then manually separate the parts from the sprues, putting the parts into a storage bin. It was a very manual process. Plus, there was a risk of the sprues freely moving around in the bin prior to sorting and marring other parts as they dropped in. ARBURG engineers tried to create an end-of-arm tool using suction cups to grab the part, but the angles and the area inside of the part didn't allow enough room for the part to be grabbed. As they say, practice what you preach. So we turned to 3D printing. A multi-material tool was created. They used a rigid frame and a flexible internal TPU bladder. Lastly, they added air connections to the rear of the tool to inflate and deflate the bladder. The tool is inserted into the part, the bladder expands and presses against the part, creating enough pressure to hold it steady as it's removed from the mold and placed on a conveyor belt. 3D printing gives designers the freedom to create and solve those issues that traditional tooling just can't. Now the process is fully automated and runs lights out and saves on labor costs. So let's take a look at this process in action. So here you can see the robotic arm. You can see it dropping the part. This time it's done as a black part instead of the green one we saw in the picture earlier. We've got a nice zoom in look at the tool itself. You can see the translucent TPU bladder right towards the left. And then here you see an injection molding tool. And this is just a one-shot version or a one material version of what Jacob was describing earlier. And as this tool opens, you can start to see, the complexity, the size, the thickness of the metal used there. You can imagine how expensive these tools get. All right, excellent. So let's move on. We'll touch briefly on 2 additional examples in our remaining time. Here you see a flip-top cap. Most of the packaging that we see in our daily lives is made of polypropylene. And from what I understand, there's a lot of challenges working with polypropylene. Jacob, maybe you can give us a quick overview of some of the challenges we might run into.
Yeah, Gerry, I'd be happy to. On top of normal injection molding process issues that I was talking about earlier, polypropylene especially, it's a very unique plastic both in injection molding and in 3D printing. I'll talk especially about the 3D printing side of things because frankly, it's just not even used. It can't be used because it doesn't really like to stick to itself very much unless it's got that very high temperature already in its interface, allowing for high bonding. But with many different substrates that you're putting it onto, it doesn't have that great of adhesion. So this is actually due to some of the chemistry side of it, where it doesn't have as many functional groups, all that crazy stuff. But really, this goes to say that like if you print it on a print pad, most of the time it will just come off. And it doesn't even like to stick to itself sometimes, for instance. But then it's also very crystalline. And what that means is if it's got a high degree of crystallinity, it can experience greater shrinkage. One thing that overcomes it with injection molding is when I'm injecting that hotter material into that mold, it may be cooling, and I may have to literally wait and compensate with additional pressure to make sure it's completely filling. But even then, you're experiencing significant shrinkage. It's a common issue, as I was saying earlier, with that steel safe kind of thing. It's something that they have to account for and just hope they get it right. But realistically, if you could turn around and, as Gerry will comment in a second with the ARBURG machine, be able to get it precise and right the first time with high consolidation, it can be a big thing when prototyping for that.
Thank you, Jacob. Yes, as you referred to, lucky for us, I suppose, the FREEFORMers extrusion process and the custom support material that we developed specifically for polypropylene has given us the ability to not only print polypropylene, but to print it reliably, accurately, and we're able to mitigate that shrinkage that you see. Here you see an example of an overmolded flip-top cap. This is printed in polypropylene and TPE. Now, you can see some cost numbers there. And to be honest, the molding costs here were calculated based on a single material mold. So doing a 2-shot mold would likely be far more expensive. But even with that advantage on the molding side of the numbers, you can see how much of a time and cost savings is gained by printing the part versus molding it. And lastly, let's take a look at a larger 2-component part. So we have a customer that was looking for a method to bypass tooling for their prototyping, similar to Wilson. However, their reason wasn't to get more creativity from their designers. It was to speed up the functional testing of their design. This is a necessary process before entering production to assure that your parts are going to perform out in the real world in the manner that they're designed to. So here you see a printed part. It's 2 sides of a drill housing and a battery blank. The customer used these parts for several tests to verify the design was acceptable and the drill would perform reliably out in the real world. Some of the testing included thermal shock, vibration, tumbling, and drop testing. The results of the printed part, when compared to a molded part, were excellent. The part performed as well as the molded part and gave the engineers enough info to move forward with their design. The takeaway here is that a printed part in the same production material something that AJ commented on earlier, we'll demonstrate similar testing results to a molded part. The key is materials to speed up your design process and to do your prototypes in the same material as your final production materials. And that's why they turn to the freeformer. So with that, I hope this session was interesting and informative. I appreciate you watching. And if you have any questions, please feel free to reach out to us, and we'll see you on the next video. Thanks.